Well, so to continue with our discussions, what did we observe in the last class? We observed that, well, to find out fugacity by using this particular equation, the equation I had already written down the equation. So finding out fugacity by using this particular equation, this was not at all very easy, and so therefore, this is the correct, this is the equation written properly. So therefore, it was important to find out a simple model from which we can find out Fi from known measurable parameters in terms of the composition. So, we found out that if we consider a mixture of ideal mixture of ideal gases, then we know that Fi bar is nothing but equals to Yip, and this is too restrictive because it neglects the interaction between the molecules. It tells us that the interaction between the molecules is negligible, which is quite restrictive, particularly if we are dealing with liquid solutions. So, then after that, what we wanted to do, we thought of doing, let us go to an ideal mixture of real gases. Now, what does this Amagat's law it suggests? It basically suggests that the volumes can be added over the entire range of pressure that we consider. So, therefore, from here we know that the total volume of the mixture is nothing but equal to your Ni Vi. Okay. Or in other words, we assume Vi bar 0 equals to, it is not 0, it can be for a real gas, that is equal to Vi. So, this on this particular basis, we write down the total volume in terms of the molar volumes. This is what this Amagat's law of additive volume states, or it states small v, it can be equal to Xi Vi. This is what it states. Now, suppose we use this particular assumptions, or rather this particular consideration. Let us see what is the expression of the partial molar fugacity that we get. Again, we start from the very basics. Suppose we have for a pure substance. For a pure substance component I, we can write it down as RT dln Fi in the pure state. So, it is just a subscript, nothing else. This is equals to Vi dP. And then in the ideal gas state, it is P, it is RT by P dP, right. On subtracting, what do we get? RT dln Fi by P equals to Vi minus RT by P dP integral no sorry, this integral and this is also integral, right. So, therefore, from there we get this integration is from P equals to 0 where Fi equals to P equals to P where the value is Fi. Here the value of Fi is equal to the total pressure, right. So, therefore, we get RT ln Fi by P equals to integral 0 to P Vi minus RT by P dP. This is what we get for a pure substance, a pure component I. Now, let us see what do we get for this same component I in mixture. For component I in mixture, what do we get? You tell me. In this particular case, it becomes RT dln Fi. This is equals to Vi bar dP, and RT dln Pi. This is equals to RT by P dP. We know it. On subtraction, what do we get? We get RT dln Fi by Yip is nothing but equals to Vi bar minus RT by P dP. If we integrate it again from P equals to 0 where Fi bar equals to Yi by P to P equals to P where Fi bar equals to Fi, this side also 0 to P. What do we get? We get RT ln Fi by Yip equals to integral 0 to P Vi bar minus RT by P dP. This was for component I in mixture, and for the pure component I, what do we get? I have just now derived for pure component I, the derivation is here. So, for the pure component I, what do I get? RT T ln Fi by P, where Fi, this is Vi minus RT by P dP, and what is this Fi equals to? This Fi is the fugacity of pure component I. One thing we need to remember very well, this Fi bar, Fi, everything is evaluated at the conditions of temperature and pressure remaining same. For both the cases, the pressure is P, and the entire integration, this and this have been done at constant temperature. Only when the pressure and temperature conditions of this equation and this equation are the same, then we can combine the two. And suppose this particular gas mixture, it obeys Amagat's law of additive volume, then what was Amagat's law of additive volume? I have already written down, it's Vi bar equals to Vi. So, therefore, if it obeys the Amagat's law of additive volume, then this term and this term, they cancel out, and then ultimately what do we get? We get, on cancellation, we get Fi by Yip equals to Fi by P, or in other words, the partial molar fugacity of component I in a mixture is nothing but equal to the mole fractions times the molar or rather the fugacity of component I in the pure state at the same temperature and pressure as that of the mixture. So, therefore, this is applicable, we find this has been derived from Amagat's law of additive volume. This is applicable provided Fi and Fi bar at same T and P, right. So, therefore, what is Fi then in this particular case? I have written down the ideal solution model here. This is the ideal solution model, where what is Fi equals to, just remember, it is fugacity of pure liquid I evaluated at temperature and pressure of solution. The only thing we need to know that this Fi cap and Fi are evaluated at same conditions of temperature and pressure. Accordingly, from this, suppose I express Fi bar by Pi equals to phi I bar, and so therefore, we know for the ideal solution model phi I bar equals to phi I, both being at the same temperature and composition temperature and pressure, which automatically implies that the partial molar fugacity coefficient, it is a function just of temperature and pressure, it is not a function of composition, which is quite a restrictive assumption. Yet, we find that from this particular restrictive assumption, it's, although it is restrictive, it gives us a very simple equation, a very simple model, which tells us that the partial molar fugacity of component I in a mixture or in a solution is the mole fraction of that particular component in solution times the fugacity of that component in the pure state at the conditions of same temperature and pressure as that of the solution. And finding out pure component fugacities for a real gas, for a liquid, these have already been discussed, and those particular equations can be used to find out Fi. Once we know Fi, we know the composition of the mixture or the solution, we can find out Fi bar. So, therefore, this particular rule or this particular law, this was first suggested by Lewis and Randall, and therefore, it is known as the Lewis-Randall model for ideal solutions. Now, here it is very important to note that it is less restrictive as compared to mixture of ideal gases, right. What does it assume? It is applicable when, just try to understand, it is applicable for a situation where the intermolecular attractions between unlike molecules are similar to the intermolecular attraction between like molecules. For example, suppose I have a binary mixture. Most of my discussions will be in terms of binary mixture, just because it is easier to conceive that. And so, that for a binary mixture, there are two components, component A and component B. The Lewis-Randall model will be applicable when the interactions between AA molecules and the interaction between BB molecules and the interaction between AB molecules are similar in nature, right. So, when does this happen? This can happen only for conditions, this can happen under what conditions? The first condition is when the physical properties of the components, they are similar. This is number one. Number 2 is when the chemical components, they are also similar. This is something very important, and we know that, see, whenever any component is in excess, what happens? Suppose again a mixture of A and B, we have a large excess of A, there we add some amount of A. So, therefore, A feels at home in the environment of A, there is very less B. So, therefore, whenever we find that at any particular pressure, if the component is in large excess, it obeys the Lewis-Randall rule. We know that at low pressure gases behave ideally. So, then normally they obey the Amagat's law of additive volume. So, for gases at low pressure it is applicable, usually it is valid for all gas mixtures, and we find that at any pressure if the component is in large excess, it obeys the Lewis-Randall rule. This is evident from this particular figure, where I have plotted the vapor mole fraction as function of the liquid mole fraction. What do I find? We find that at when the mole fraction of this particular component is close to 1, we find that more or less the Lewis-Randall rule, it is valid under this particular condition. For this particular case, I can write down the Fi bar, this is equal to Yi Fi, but let me remind you that this is done for a very low pressure. Now, for low pressures what happens? For low pressures we know that Fi, it is equal to the total pressure of the component in the vapor phase, right. So, therefore, if it is a vapor, it is a pure component vapor, then we know that this particular FIV is nothing but equal to the total pressure of the system. What about the liquid composition? In the liquid phase we have this FIL, this will be equal to Xi, sorry, this is going to be equal to Xi FIL. Now, if you recall, at low to moderate pressure, what happens to this particular FIL? This becomes, when the Poynting correction factor and the correction factor due to non-ideality of the gas, the vapor phase is there, can be neglected, this reduces to Pi saturated, right. So, therefore, from here what do we get? Under equilibrium conditions we know FIL equals to FIV. So, for low to moderate pressures what do I get? The equation becomes something like Xi Pi saturated equals to Yi into P. And I guess this equation all of you already know, you are aware of this, you have been doing this from your school days, this is nothing but the Raoult's law, right. So, therefore, under what conditions are this applicable? I repeat, at low pressure for gases we behave ideally. This is usually valid for gaseous mixtures. It is valid for any pressure if the component is in large excess. When we find that the component is in large excess, then the linearity is maintained in this particular condition. And we also notice for this particular condition, we find that more or less we can write it down as your Fi bar, it is proportional to the composition of the mixture. And we know that for when the component is in large excess, for this particular portion, more or less this particular proportionality constant, this is equals to the fugacity of the pure component situation. Now, before I proceed, I would just like to bring your attention to another particular aspect of this graph. What do we observe? We observe that the graph, it exhibits some sort of a deviation from Lewis-Randall rule, which we will be discussing later. This shows that it exhibits non-ideal behavior over a large range of composition. We are not going to deal with it at the moment. At the moment, we will just be dealing with the ideality portion. We find that it is ideal under this particular condition. Here the relationship is linear, and we know that this particular relation holds under that condition, right. So, therefore, for this particular condition we can write Fi bar is proportional to Xi, fine. Now, let us notice the other extreme, when the component is in very less amount. Just observe this portion. We find that in this case the slope or the nature of the curve is completely different as compared to this case. but if you slightly extrapolate this thing, you will find that, and if you keep on extrapolating this, we find that at very low concentration, that when the concentration is almost equal to 0, under that condition also there is the linearity part holds, or in other words this equation holds under that case. But for very low concentrations, the proportionality constant is not equal to the pure component fugacity at the temperature and pressure of the mixture. So, therefore, we know that for high concentration of component, F, the partial molar fugacity is proportional to the mole fraction, or Fi bar equals to Ki Xi, where this Ki is nothing but equal to the pure component fugacity. We also know that for very low concentration of the component, when say Xi is almost equal to 0, under that condition also we find Fi bar is proportional to Xi. But in this particular case, or in other words Fi bar equals to Ki Xi, but in this particular case this Ki is not equal to Fi. On the other hand, this is some other proportionality constant which is known as the Henry's constant, or it gives the Henry's law for infinitely dilute solutions. So, therefore, we have the ideal solution which gives you, and the ideal dilute solution. For both the cases, what do we have? Fi bar is proportional to Xi, but for ideal solution, or in other words Fi bar equals to Ki Xi, but for ideal solution Ki equals to the pure component fugacity. For ideal dilute solution, it is the Henry's constant of component I in the solvent. So, this is something very important which I wanted to show you. Well, what about the other thing? We found out then it is usually valid for gaseous mixtures, as I have mentioned. It is rarely valid for liquid solutions, because remember one thing, what is the basis of the Lewis-Randall rule? The Amagat's law of additive volume. What is the basis of Amagat's law of additive volume? It assumes that the interactions between the molecules are same when it is in the pure state as well as in the solution. This is quite applicable for gaseous mixtures, where in any case the interactions are very weak. So, therefore, for gaseous mixtures very safely you can assume the Lewis-Randall rule, even if the gases are not ideal. Remember, the basis is ideal mixture of real gases, it is not an ideal mixture of ideal gases. But for liquid solutions, where the interactions are very important, for very few situations you will get that the interactions between like molecules is similar to the interaction between the unlike molecules, or in other words interactions between AA molecules and BB molecules will be different from the interaction between AB molecules for most of the cases of a binary solution of A and B, right. So, therefore, in this particular case we find that in liquid solutions Lewis-Randall rule it is applicable when we find that the component molecules are similar in size and in chemical nature. For example, isomers, adjacent members of homologous series, for example, benzene toluene mixture, for heptane hexane, for such mixtures it is applicable, and also for isotopically substituted compounds. For example, suppose you have C6H6 and C6D6 deuterium. So, for such type of things only the ideal solution model is applicable. For most of the cases it is not applicable, but we need to remember, just like ideal gases, ideal gas equation, it is not applicable for most of the cases, yet we have it, and when the gas deviates from ideality, we have tried to incorporate some sort of a correction factor in order to incorporate the deviation from ideality. We had incorporated the compressibility factor. The normal ideal gas equation for 1 mole of the gas was this, and for a real gas we suggested the equation in this form, where Z is the correction to the ideal gas equation to take into account the real gas behavior. In this particular case also, knowing fully well that it may not be applicable for liquid solutions, we consider the ideal solution model. We are going to discuss the characteristics of ideal solution model, and once we have understood ideal solution model, we would try to see what are the corrections and in what way the corrections can be incorporated into the ideal solution model to account for the behavior of, or to account for the non-ideal behavior, right. So, therefore, let us discuss the properties of the ideal solutions before we proceed. So, therefore, what are the different properties of ideal? There is one interesting thing that which I would like to say. Well, this is something very interesting, that usually we feel that when the gas is at higher pressure, where it exhibits liquid like density, the fluids they tend to mix with little or no change in volume. That is quite evident. So, we are always tempted to think that therefore, when the gas is at high pressure, then it should be obeying Lewis-Randall rule, and therefore, we can apply Lewis-Randall rule for gases at high pressure. Although at the first thought it seems to be probable or seems to be correct, at second thought we are reminded that this is not always correct. Why? If you observe this graph, what do we see? This is a compressibility factor chart for nitrogen butane mixture at 171 degree centigrade. What do we find? That at 690 bar more or less, we find that it is a linear function. So, therefore, we are tempted to think that well, at 690 bar we can use the Lewis rule, because under this particular condition V I is a linear function of mole fraction. But we need to remember that the V is inside the integral. If you remember, the equation is R T d ln f I by y I p, which is equal to 0 to p V I bar minus R T by p dp. This particular V I bar, it is inside the integral sign, right. So, therefore, it is important that V I bar or the Amagat's law should not only be obeyed by at 690 bar, it should be obeyed from 0 pressure to 690 bar pressure. At 690 bar, the Amagat's law is valid, right. So, therefore, you might think at 690 bar we can use it, but if you slightly come to lower and lower pressures, you find that below 345 bar the linear variation or the additive property of volume is no longer applicable in this particular case. So, therefore, in this particular zone, if you find in this particular zone we find that the additive property, it fails completely, but at the same time we need to remember that we want the additive property to be valid right from 0 pressure to 690 bar pressure. So, therefore, just being applicable or just obeying the Amagat's law of additive volume at any pressure does not guarantee that we can use the Lewis-Fugacity rule at that pressure, because for using the Lewis-Fugacity rule we need to consider this particular integral where the volume is inside the integral sign, and therefore, it requires the law of additive volume is required to be followed not only at the pressure of interest, but over the entire range of pressure from 0 to the P. So, therefore, this has to be considered with caution. Well, so now let us come to the property of what are the properties of ideal solutions. Let us see, we have already assumed that the mixture satisfies the Amagat's law of additive volumes. What is that particular law? It is V I bar equals to V I. Fine. What is the Lewis-Fugacity rule? It is F I bar equals to X I say F I. Fine. Now, if you recall, in the last class we had, or maybe in few classes back, we had tried to we had found out the variation of fugacity with pressure and the variation of fugacity with temperature. Therefore, did we found? We found out that del ln, from that equation we found out del ln f I del p at constant T and total mixture, this would be equal to V I bar by R T. Same way, from using this equation we can write down del ln f I del p at constant T n, this is nothing but equals to V I by R T. So, we know that if V I bar equals to V I, from there we got the equation. So, therefore, the first property is that ideal solutions are formed with no change in volume. So, therefore, there is no change in volume when ideal solutions are formed, right. What are the other properties? We will be discussing the other properties in the next class.